In this video, I'm going to walk you through lesson 13 of unit 8.1. And I will tell you, I am going to trim this one down. And as I go through it, I'm going to share with you how I would trim it. It says it's 3 days, and it's because it's a lot of teacher facilitation to kind of pull the ideas out of students. But we've been in this unit for a long time. So I don't normally do this, but I'm going to share some commentary along the way of how I would trim this lesson. Okay, so we start by looking back and we navigate into the lesson by considering those common structures we observed from the last lesson. The structures we looked at, they were cotton and foam, and we looked at those close-up pictures, and we were talking about what they had in common for those top performers, those that were good at reducing the peak forces. And what we realize is that they all had these structures that had space in them. And as we're going through and we're talking about this, it suggests making a class poster. It looks like this. I'm not sure that I would spend the time doing this because we already looked at them. I mean, really, the big idea is, oh my gosh, they've got space in the middle and some of them look like rings. Where we're trying to push them is that it looks like rings. Now, what I would do would probably be have my top 4 performers or 6 performers make this poster, share it with students, and then we would talk about how could we make a model that would represent this so we can kind of figure out why these spaces are reducing peak forces. So really this is a navigation moment into making a scale model. So I don't think the sense making is worth it to go through this poster. It's very time consuming. So then we realize, okay, let's make up some scaled up models of what we can't see with our eyes. And so we're going to make a physical representation, and we're going to use, this is plastic from a file folder, so it's pretty durable. It's more rigid than paper, and you cut these strips and then you tape them in rings and then you tape the rings together. So these represent those spaces that we saw inside the material. So this is important before we watch the next series of videos to talk about why we're using these rings. And it's because it resembles the structures we saw in those top performers. Okay, so the next section, we're going to be watching 5 videos. Now, the teacher guide has you go through them one at a time and pull out ideas from students. But to be quite honest, I think I would have maybe do the first one together, and then I would put these on an LMS and I would have them watch them either individually or with a partner. Headphones are wonderful. It makes the class quiet. So go ahead and watch these, or you can play them in front of the class. Have them make observations, and then at the end, you're going to have a discussion and try to pull out these key ideas. But I'm going to just kind of walk you through what each one is. Here's video A. This one is a plunger that's going down the ramp and hitting the brick with no rings. This one is very similar, but it's going down the ramp and it's hitting a ring that's attached to a brick. So then it says write down observations and talk about some stuff. I would just keep going. I would point out though, look at the plunger markings and watch how much the ring deforms. So if you can kind of pull that out as they're watching, walk around the room. And do you notice anything about the ring deformation? Do you notice anything about the markings or how much peak force? And so they can look for those things in the video. In video C, it's going to be also 1 ring, but this time the ring is attached to the plunger and not to the brick. Video D, we have 2 rings attached to the brick. And video E, we've got 2 rings attached to the plunger. And the patterns that we find out, let's go ahead and look at this. The patterns that we find out are that the rings provide space for the protective material to deform. The more of the structures, the more cushionier it is. The longer the contact time in the collision. The more of the structures, the lower the peak force that are produced by the collision. And also, this isn't as important, but when weaker forces are applied to an object, it will take more time to change motion. And when stronger forces are applied to an object, it will take less time to change motion. But what we really need to know is this. The more structures there are, the cushionier it is, the less the peak force. That's all we need to pull out of these 5 videos. And I think you can do that pretty quick. Now we update our progress trackers here. I would probably skip this and just keep going. Okay. Then we're going to develop free body diagrams that go along with these videos. And so I'm just going to show you the answer key. There is a handout right here. You print them out for students. Let's just look at this answer key. I would probably have them do this in partners and then try and then go over it as a class. And so you're going to have nothing between the objects, one ring on either object, and then they're going to continue to go on. Okay, that would probably be a day. So now we use these ideas to consider a space or shape constraint for cushioning material, because very likely you only have a certain amount of thickness you can use for a cushioning material. Helmets can only be so thick. Well, I guess that's a good related phenomenon. If you look at football helmets, the ones that are used in practice now to reduce concussions, they're really thick. So the more cushion you have, the more it reduces peak force. But you are not going to sell football helmets that are, a foot of cushion around it. You're also not going to sell any cell phone cases that have, so much cushion that you can't fit it in your pocket or you can't fit it in your purse. And so we're thinking about like how much cushion we can actually put on and also the amount of space. Now, one way to think about reducing the amount of cushion is like maybe we just put cushion in the corners of the phone case. And so we're going to explore the effect of that. Again, I'm going to skip this progress tracker. I'm going to keep going. So here is a lesson handout. We're going to explore the shape of the cushioning material. Do you want it to be like on a single point, or do you want it to have, a big space? So let's say that this is the phone beneath and this is the pressure of the collision on top. And so which kind of structures work the best? Now, this one you're supposed to set up and go through and do as a demonstration. But I think what I would do would be, I would take a picture of this happening and I would print them out and put them in lab stations. I would also give them the materials that they can play with and explore, but I would like to give a picture of what it really is supposed to look like in case they can't get there. And then I would have them make some observations so that you're not going to go through these one at a time in a drawn out way. Just like the videos, work with a partner. What do you notice? What patterns? What observations? So after that, we have a demo and going to connect what we saw with the rings to spring scales. And so you do a demo replacing the rings with one spring scale, two spring scales. It looks like this. And you have that plate with the weight on top. And we're looking at, with two spring scales, the peak force is spread between the two. With three spring scales, it's spread between the three spring scales, and the peak force is reduced on each, just like the three rings. So that could be a quick demo. But really what we're trying to figure out is that the surface area matters. And we can demonstrate this easily by using a piece of styrofoam. And when you place weight on top and figure out that one contact point, if I put it on top of one spring scale plunger and put weight on top, it's going to make an indentation. You can use something else, like something that's going to be a little more rigid, like the end of a pen or a pencil. You put one down and put weight on top, it's going to make an indentation in the styrofoam. If I spread it out of three pens or three spring scales, the indentation is going to be less in the foam. So we're showing physically that the more space you have, the more surface area, the better it works. And so you do not want a cell phone case with just the four corners, because that's going to put a lot of pressure on those four corners. You want it spread out as evenly as you can across the surface area. So that's the big idea here, is that one, we want a cushioning material that has a lot of little cells in it that can deform, a lot of little structures. We also want it to be spread out over the surface area. That's really all you need out of this lesson. It's a great way to get there, but this is a pretty long way to get there. So after all of this, it's the teacher guide suggests to update the progress tracker. I think what I would do is go through all of these progress tracker answer keys, and I would figure out maybe what the key ideas are and put them onto a chart paper that they can think about and reference as they design their final solution. That would be a whole lot easier. So just develop a class poster, some key ideas that we figured out. Remember, the main things are the more structures inside that can deform, the better the cushioning material. But honestly, we kind of already figured that out, that we will use the top performers as our cushioning material. Now we just can explain why they work, but we just need to pick the top performers in the first place. And then second of all, that we want the surface area to be spread out. Those are the big ideas here. That's it. So you decide how you want to go through this, but I definitely think this could be trimmed down quite a bit. So at the end, we're going to make connections to our own designs. And I would say I would do that as I was going through that class poster, these progress trackers, what the big ideas from this lesson. I would be talking about the design, solution the whole way through. And then you can connect it to the anatomy of a bike helmet. And this is a handout. It's a reading. And we just talk about, connections to the brain. This has a little bit more of that life science standard in it too, with talking about the brain. But here you go. We're talking about the foam and why it needs to, be used in helmets to help protect our head. Okay. That was a lot for lesson 13. Again, I hope that helps you trim it down. We need to get this unit wrapped up and we need to create our final designs in lesson 14. But before we do that, let's talk about the materials prep in the next video.